Okay, so the first draft for the November exams is out now. So I've got some important dates for you. So firstly, with Math 161. Okay, so Math 161 finishes on the 21st of October. Okay, so this will be for class test 4, and then we're done. Yep. Then 2 weeks after this, you have your physics exam. Okay, so after maths, 2 weeks, then you have physics 163. Okay, this will be on the 6th of November, 9 a.m. Okay, then 1 week after that, you have Math 142. Okay, that will be on the 13th of November. Okay, and then 1 week after that, you have Math 161. Okay, that will be on the 18th of November. Okay, so this is a first draft. It may change, but, prepare your study timetable for this. And then if there's any changes, it's not so bad. Okay, but please note they're like 1 week apart here. So, just keep that in mind. Okay, so the lecture for today, we're going to finish off the series convergence tests. So remember, we had the 10 of them that you could use. And, some of them you can use one method, some of them you can use 3 different methods. It depends on the question that's given. So we've got 12 problems here. I'll go through all of them using one of the methods. And then after that, I'll show you which methods to do for homework. Okay. So example number 1. Okay, we have the sum. N goes from 2 to infinity, 1 over the natural log of n. Okay, so whenever we have something like this, where it's a bit more complicated, the first thing you should try and do is compare it to something that we do know, right? So 1 over the log n, we don't know what that is. That's pretty complicated. But 1 over n, we do know that. We know that one diverges. So let's try and compare the two. So we know that n is greater than log n, right? You can just see that from the graph. So if we look at the function y equals x, it looks like this. And log x, that looks like this. Right? So the x function is always above, so that means n is always greater than log n. But we want 1 over n and 1 over log n, so we take the reciprocal. So 1 over n is less than 1 over the log n. Okay, now we can compare them. So 1 over n, that's the smaller one. So let's have a look at that. So we have the sum, n goes from 2 to infinity, 1 over n. This diverges. All right, so P series test. In this case, P is 1, so it diverges. And if the smaller one diverges, the one on the left there, then the larger one also diverges by the comparison test. So 1 over the natural log of n also diverges by the comparison test. Okay, or direct comparison test, that means the same thing. Okay, again, you could have said direct comparison test. Okay, so depending on where you look, you'll see the 2 different names there. All right. Any questions for this one? No. Okay. You can try integrate this. So if you have 1 over the natural log of x, you might be able to integrate that. But that's a lot more difficult than this. Okay. So this should be your first step. And then, later on, try something else. Okay, number 2, we have the sum n goes from 2 to infinity, 1 over the natural log of n to the n. Okay, so a little bit more complicated. Now this n to the n is going to give us some trouble inside there. But remember your log rules. If you have log of some base to an exponent, the exponent can come out. So we can rewrite this as the sum n goes from 2 to infinity, 1 over n log n. Yeah, so we have something like this. Now, if we replace the n's with x's, this is very easy to integrate. So we're going to use the integral test. Okay, so we replace n with x and get our function f. So that will be 1 over x log x. Okay, and that's pretty easy to integrate. But first, we need to check the 3 conditions. Number 1, is f continuous? Yeah, x continuous, log continuous, no issues there. F must be positive. Yep, that's fine, it's positive. And lastly, f must be decreasing. Well, the bottom part is increasing, so 1 over that must be decreasing, so everything's fine. So f continuous, check. F positive, check. And f decreasing, check. Okay, so we checked all 3. Now we can do the integral. So this is going to be the integral from 2 to infinity of 1 over x log x dx. Okay. Now this is an improper integral, so we need to do the limit for that top part. So this will be the limit as b goes to infinity, the integral from 2 to b, 1 over x log x dx. Okay. Now we ignore the limits, do the integral, and then take the limit at the end. So this is going to be equal to the limit as b goes to infinity. It's quite easy to do. This will just be the log of x. Okay, and that will go from 2 up to b. Then we can substitute the bounds and then finally take the limit. So this is going to be the limit as b goes to infinity, the log of b minus the log of 2. Okay, but that's just a constant. We don't care about that. When b goes to infinity, log goes to infinity, so this whole thing diverges to infinity. And if the integral diverges, then the series diverges. So the integral from 2 to infinity, 1 over x log x dx diverges, clearly. And if that diverges, then the series also diverges. Any questions with this one? Yeah. Pretty straightforward. Okay, number 3. Let's have a look at this one. So here we have the sum, n goes from 1 to infinity, of minus 1 to the n over tan inverse n. Yeah, so we got something like this. Now here, we're not going to try to compare this to anything. That's going to be quite difficult. Also, it's alternating. We've got that minus 1 to the end there. So we use the alternating series test, right? If it's alternating, we use that test. Okay, so we ignore the minus 1 to the n. Whatever's left over, we call bn. So that's 1 over tan inverse n. Okay, now we need to check, is this bn without the alternating part, is it decreasing, and is the limit 0? Okay, let's check the limit. So when n goes to infinity, what will the limit be for that arctan? Pi over 2. Yeah, so the limit's going to be, for the bottom part will be pi over 2. We have 1 over that, so 2 over pi. So limit n goes to infinity, 1 over tan inverse n. That's 1 over pi over 2, 2 over pi. That's definitely not 0, so it diverges. Okay. Any questions for this one? They're all good. Okay. Number 4. We have the sum, n goes from 1 to infinity, of 2 to the n over 3 to the n plus n cubed. Okay. This one's a bit more complicated because we've got exponents and powers, n cubed there. Yeah? Yes. So you just disregard minus. Yeah. You throw that away, and you look at whatever's left over. So here we can go back to the lecture 27. Alternating. There we go. So for the alternating, we have minus 1 to the n bn, and we only look at the bn part. We don't look at the minus 1 to the n. Okay. So this whole thing was an, and then if we get rid of the minus 1 to the n, that's our bn left over. Okay, so this one's a little bit more complicated. Got exponentials and powers there. So what we want to try to do is compare this to something that we do know. Okay, that's always the first step. Now, if we get rid of that n cubed at the bottom, then we have 2 over 3 to the n. That's a geometric series. We know how those work. So let's get rid of the n cubed and look at the result. Okay, so we're going to have 2 over n over 3 to the n plus n cubed. We get rid of the n cubed. Okay, that makes the thing on the right larger. So that's going to be less than or equal to 2 to the n over 3 to the n. Right? You get rid of it, then the thing on the right will be larger. Now, 2 to the n over 3 to the n, we can write this as 2 over 3 to the n, right? Just exponents. Now, if we take the sum of that right-hand side, that's just a geometric series. So we have the sum, n goes from 1 to infinity, 2 over 3 to the n. That's a geometric series. The ratio is less than 1, so it converges. Converges by geometric series test. You can abbreviate that if you want. Since we have r is less than 1, right? We have 2 over 3. Okay, so that means the larger series converged, which means the smaller one must also converge. Okay, so the one on the right, the larger one, converges by the geometric series test. So the smaller one on the left also converges by the comparison test. Now for homework, you're going to try this again using the limit comparison test with that geometric series. So homework, use limit comparison test with the sum n goes from 1 to infinity, 2 over 3 to the n, which we know converges. So when we do the limit comparison with this and the one that's given, if we get some finite number, positive finite number, then we know they both converge. Okay, so check that out for homework. Okay, any questions with that? All good. Okay. Number 5. Okay, we have the sum, n goes from 1 to infinity, of n sine squared n over n cubed plus 2. Okay, So here you get your first little hint for what to try first. Okay, so I'll put little hints on the side. If you see these, it's best to follow them. Whenever we have trig functions like sine squared or cos squared, we can always make it into an inequality and use the comparison test. So here we know that sine squared n is less than or equal to 1. So we can replace that with 1 and we get an inequality. Or if we have cos squared n, that is also less than or equal to 1, and we can make an inequality out of that. Okay, and then once you've done the inequality, you can use the comparison test. Okay, now these are just hints at how to solve it. You don't have to follow it, but it's a good step to follow. Okay, so let's do that. So we've got sine squared, so we're going to use that first inequality there. So sine squared n is less than or equal to 1. Okay, that's the starting point. But that's not what we have. We've got n sine squared over that. So let's times both sides by n. Okay. And then at the bottom, we've got n cubed plus 2. So let's divide both sides by that. So we've made it simpler. And we get this series on the right here. Okay, n over n cubed plus 2. Now for homework, to check if this one converges, you can integrate that. So replace n with x and integrate. Remember to check the 3 conditions. So homework, check using f of x equals x over x cubed plus 2. Okay, it's more difficult, but you can try it out. It's good to know multiple methods. We're not going to do that here. We're going to do it a little bit easier. If we get rid of the 2 there, the fraction is going to become larger. So this is less than or equal to n over n cubed. But n over n cubed is just 1 over n squared. And we know that one. That converges by the p-series test. So we have the sum. N goes from 1 to infinity. 1 over n squared. That's the larger one, right? It's on the right-hand side. So the larger one converges by p-series test. Okay, in this case, p is 2. Okay, so the larger one on the right converges. So that means the smaller one on the left also converges. Okay, so this one also converges by the comparison test. Okay. Any questions for this one? Okay, and again, if you didn't see this bit with inequality to get to 1 over n squared, you can try integrate this to see if it converges. It will converge, we know that, but just doing the integral to see if you get some finite number, you can try that for homework. Okay. Any questions before we move on? Oh, good. Okay. That was 5. Number 6. Okay, we have the sum. N goes from 1 to infinity of minus 1 to the n over roots n plus 1. Okay, so we got this. What do we use? Alternating. Yeah, we use the alternating series test. Right, it's no use using something else. It's alternating, so use that one. Yeah, so we ignore the minus 1 to the n. The leftover part we call Bn. Yep, so we got that. Now we need to check, is it decreasing? Is the limit 0? So when n gets larger, the fraction gets smaller. So obviously it's decreasing. So check. And lastly, when n goes to infinity, the bottom goes to infinity, the fraction goes to 0, so the limit is 0. So check and check, it's convergence. As n plus 1 is convergence. Okay. Remember, there's always the 2 checks. If one of them fails, you got a problem. Okay. Any questions for this one? Oh, good. Okay. 6, 7. Okay, so here we have the sum, n goes from 1 to infinity, of 1 over root n minus 1 over n. Okay. Now here it's written as 2 fractions. It's best to have it as a single fraction for us to work with. So instead of having 1 over root n and 1 over n, we're going to have something over n times root n. Okay, to get the same denominator. So this is going to be the sum. N goes from 1 to infinity. Yeah, right, we want the same denominator there. So this is going to be n minus root n over n root n. Okay. So we've got something like this. Okay, now that it's a single fraction, we can then do our comparisons. Okay, so what can we do with this? We can do a comparison with something. So let's try and make this a bit simpler. If we get rid of that root n over there, then we've got n over n root n, right? Okay, which simplifies to 1 over root n. Is that convergent or divergent? One over n to the half. P is a half. Convergent or divergent? I'm hearing different things. Divergent, yeah. So we got P is a half, so it's divergent. So we ignore that stuff on the side there, and we're going to compare this to 1 over root n, which we know is divergent. So we're going to compare with sum n goes from 1 to infinity, 1 over root n, which we can write as n to the half. Right? That gives us a p of a half, so it diverges. Which diverges by p series test. Okay, and we have p is a half. Yep. Question? Yeah. You just ignore the minus root n and simplify.
Yes, when you see when you get a question.
Yeah.
Just
Yeah, you just ignore that. We'll see it later. For example, if you have n squared, I'll write it on the side here. If you have something like n squared plus 2n plus 1 over n squared minus n plus 2, we're taking the limit as n goes to infinity. This limit is just 1, because we can ignore all the smaller stuff, and n squared over n squared is 1. It's like that. So in the limit, we ignore all of the smaller stuff. Okay. Like n and root n, we ignore the smaller one. Okay, so here we ignore smaller terms. In the same way, we can cancel those smaller ones for the limit to be 1. Yeah? Yeah, exactly. Yeah, exactly. So here we've got n squared, and then smaller powers, you ignore it. And at the bottom, n squared and smaller powers, you ignore it. So here we've got n and n to the half. So n has power 1, the other has power half, you ignore it. Okay, we know this one diverges because of the p being a half. So we can use the limit comparison test. If we get a finite number, then we know both of them diverge. Okay, so we're going to have the limits as n goes to infinity. We can put the one that we do know, the 1 over root n at the top, over the one we don't know, we can put that at the bottom. Okay, so we get this mess. And then from here, we can just take the limits. If we get some positive finite number, we know that both of them then diverge. So let's check. So this will be the limit n goes to infinity. Here we have a fraction over another fraction, so we can flip those around. So this will be 1 over root n, n root n at the top, and n minus root n at the bottom. Okay. Now the root n at the top, root n at the bottom, they can cancel. So this gives us the limits as n goes to infinity of n over n minus root n. Again, smaller powers we just ignore. N over n, that's 1. Okay, and 1, that's positive, it's finite. So a limit comparison test tells us that both diverge. Therefore, both diverge using the limit comparison test. Okay. Again, here the L value. Okay, positive, finite, so both of them diverge. All right. Any questions for this one? No, all good. Okay. Number 8. Okay, so here we have the sum. N goes from 1 to infinity. N to the n over 3 to the n squared. And here we get our second law hint. Okay. Whenever the top and the bottom have powers of n, you use the root test. Okay. So in the top, we have n to the n, so n is in the exponent. In the bottom, we have 3 to the n squared. Doesn't matter if it's squared, there's n there. So power of n at the top, power of n at the bottom, you use the root test. Powers of n means use root test. Okay, so you know exactly what to use if you see something like this. You don't have to think about it. Okay, so let's use the root test. We take all the stuff there, the an, and raise it to the power 1 over n. So we have the limits as n goes to infinity, all of the stuff inside, n to the n, 3 to the n squared, to the 1 over n. Okay. We take the 1 over n inside, take the limit, see what we get. So this is going to be the limits as n goes to infinity. N to the n and to the 1 over n, that will just be n to the 1, so n. And at the bottom, the 1 over n will cancel the 1 from the n squared, so we just have n left over. Okay. We take the limits. Obviously, this will just be 0. Okay, but 0 is less than 1, so it converges by the root test. So therefore, the series converges by the root test. right? Because our limit value there was L is less than 1. Okay. Remember, L less than 1 converges, L greater than 1 diverges, L equal to 1, try something else. Okay, remember, it was those 3 things. All right. Any questions for this one? Oh, good. Okay. Number 9. Okay, so this is the sum. N goes from 1 to infinity, n to the n over n factorial squared. Okay, so now notes at the top there, we've got a power n. So you might think to use the root test from what we said above. But now this next hint goes above that. Whenever you see a factorial, you use the ratio test. Always. No matter what the other things are. Okay. So even though there's the power n, if there's a factorial, you immediately use the ratio test. So if there's a factorial, use the ratio test. Okay. So let's use the ratio test. Okay, so we're going to have the limits. N goes to infinity. We need to take the next term, so n plus 1. So wherever you see an n, you put an n plus 1. So this will be n plus 1 to the n plus 1 over n plus 1 factorial squared. So that's the an plus 1. Then we need to divide by an. So we can multiply by n factorial squared over n to the n. Right? If you divide by a fraction, you can just flip it. Okay. Now this looks horrible, but we can simplify. So we just go step by step. So firstly, something squared is just the something times itself. So even though it's factorial squared, don't worry, it's just the something times itself. So let's do that. So this is the limit as n goes to infinity, n plus 1 to the n plus 1. N factorial squared is n factorial times n factorial. It's just squaring. Okay, same thing with the bottom. N plus 1 factorial squared is n plus 1 factorial times n plus 1 factorial. And the n to the n, that just stays. Okay, so that's the first bit done. Next, what does it mean to have n factorial? N factorial is n times n minus 1 times n minus 2 all the way down to 1. So n plus 1 factorial is n plus 1 times n factorial. So just think about that. So this will be the limits as n goes to infinity, n plus 1 to the n plus 1, n factorial. And then the bottom, we can write that as n plus 1, n factorial. Yeah, like 5 factorial is 5 times 4 factorial. You can write it like that. Then we do the same for the other one. So that's going to be n plus 1, n factorial. And we still have the n to the n. Okay, so we've expanded out quite a bit. Now we can start cancelling. In the top, we have n factorials. In the bottom, we have n factorials. They can go. Okay, top and bottom, we can cancel that. Next, n plus 1 to the n plus 1. We can rewrite that a little bit. So that will be the limit. N goes to infinity. N plus 1 to the n times n plus 1 to the 1. Okay, we've just separated it out. All over. N plus 1, that's going to stay. and n to the n, that's going to stay. So we've got this. Next, n plus 1 at the top, n plus 1 at the bottom. They can cancel. So now we have the limits as n goes to infinity of n plus 1 to the n over n to the n. Which one? Oh, yeah, n plus 1. Thanks. Yeah, so the one from the top cancels the one from the bottom. Yeah. Okay, so let's get rid of that. So we have n plus 1 to the n at the top over n to the n, let's keep that in the bottom there, times 1 over n plus 1. Okay, so why am I doing that? Well, the two powers of n we can group together. So this is going to be the limits as n goes to infinity. We can put that together. So n over n, that will be a 1. Then we have 1 over n to the n times. Now I'm going to do the limits separately for each one. Right? Remember your limit laws. So this will be the limits n goes to infinity of 1 over n plus 1. Yeah. Now the first one, we covered that last year with L'Hopital's rule. That's going to be E. And the second one, that's easy. When n goes to infinity, that's going to just be 0. Okay, so here, for this one, we use L'Hopital's rule. Okay, look at your notes from last year if you don't remember that. Okay, so the first one's E, the second one's 0. So it's just 0. Okay, but 0 is less than 1, so it converges. By the ratio test. All right, we have L is less than 1. Okay, so a lot of algebra stuff in the middle, but you know, the idea is pretty easy. You take an plus 1 over an and take the limit. Whether you can do the algebra and the limits, that's on you. Yeah. So please, limit laws, squeeze theorem, L'Hopital's rule, you have to know those. Any questions? All good. Okay, next one, number 10. Okay, here we have the sum, n goes from 1 to infinity, of sine 1 over n squared. Okay, pretty complicated, but that thing inside, we know what that is. The 1 over n squared, immediately we know that one converges. So we know the sum, n goes from 1 to infinity, 1 over n squared, converges by the P series test. P equals 2. Okay, so we know it converges, P is 2, that's fine. So we have something that we don't know, and we have something that we know. What can we do? Take a look. What's the ratio of the two? We have something we know, something we don't know, and then we do something. The limit, exactly. Okay, so we're going to do the limit comparison test with the thing that we don't know and the thing that we do know. So this is the limits, n goes to infinity. We can write it as the thing that we don't know. That's the sine one. We can put that at the top. Okay. So that was like the an, and then the bn is the one we do know. We can put that at the bottom. 1 over n squared. Okay, now written like this looks very confusing, but we're going to do a little change of variables, and then it's exactly something we've seen before. So we're just going to say x equals 1 over n squared. right? Because we have 1 over n squared at the top, 1 over n squared at the bottom. Let's just call that x. Okay, when n goes to infinity, what happens to x? N goes to infinity, x goes to 0, yeah. Those will be limits, x goes to 0, sine of x over x. And we've seen that before. What's this? Sorry? Sine x over x with the limits. What value is that? We did it before when we did the L'Hopital's rule and the squeeze theorem and all that. Oh, someone said? 1. Yeah, it's 1. Okay, so the value is 1. It's a finite positive number, so that means they both converge. Because the one we know converges, we got a finite limit, so both converge. Again, limit law, squeeze theorem, L'Hopital's rule. You're doing limits for a lot of these things, you need to know those. Both of them converge. Right? So limit comparison test, you're going to be doing limits. Ratio test, you're going to be doing limits. The root test, you're going to be doing limits. That's 3 out of the 10 you have to do limits for. Okay, very important that you know your limit laws. Both of them converge by the limit comparison test. Right, the limits, that was L, finite positive, so converges. Right. Any questions for this one? Okay, again, the aim is always to compare to something that you do know. So whatever complicated thing that's given, you try to simplify it down to something that you know, or you compare it to something that you know. It's only those two. Okay. So you simplify using like the comparison test to something that you know, or you compare it. Any questions before we move on? All good. Okay. Last one, number 11. Okay, sum n goes from 1 to infinity, cos pi n over the natural log of n. Okay, now for this one, we need to think a little bit about this cos pi. When n is 1, we have cos of pi. What value is that? Negative 1. And when n is 2, we have cos 2 pi. What value is that? 1. And the next one's going to be minus 1. Next one's going to be plus 1. It's alternating. So we have the sum, n goes from 1 to infinity. We can write it like this. Okay, so it looks complicated with the cos pi and so on, but this is the same thing as minus 1 to the n. It just alternates. Okay, now we know it's alternating. We just use that alternating series test. So we ignore the alternating part. The leftover we call Bn. That's 1 over the natural log of n. Okay. This is decreasing. The limit is 0. It's convergence. So decreasing, check. We can take the limits. 1 over the natural log of n. That's 0. Check. Okay, you only have to check those two. It's convergence. Is convergence by the alternating series test. Okay. Just a bit on the tutorial, then I have to say something about the quiz, and then we can go. Okay, the tutorial. Okay, it's split up into several exercises. So each of these exercises here focus on one of the tests. Okay. So this first exercise, 11.2, that is only on the geometric series test. Okay. So for all of the questions, you know exactly what to use. You use the geometric series test. So it's something like this. So you find the R value and then you check if it's convergent or divergent. Okay. Then the next one, 11.3, that is only on the integral test. So all of them you try and integrate. Okay. So you can go through these from 11.2 to 11.6 if you need revision on any specific one. So if you need more help with the ratio test, you look for that one and you do that. Yeah. So that's the practice stuff. 11.7, those are the mixed problems. In other words, it doesn't tell you what to use. They just give you the problem. So I'll show you a couple. 11.7. Okay, so these mixed problems. So for example, this first one, the 1 over n, we know it diverges. We can compare it to, this one's given. Okay, this one's given to us here. And we can use the comparison test. You could have also tried to integrate it. You could also try with the limit comparison test. So these last problems, the 11.7, there's more than one way to do it. The other ones, there's only one way. Okay. Another example, let's see here. Like this one, the k squared over e to the k. You could try integrate that, right? If you replace k with x, you end up with x squared e to the minus x. Right, you can integrate that. But here, I did the ratio test. You get the same answer. Okay, so again, this last one, the 11.7, it's all mixed. You can try multiple methods, but these top ones, 11.2 to 11.6, that's if you need help with a very specific one. Okay, but if you're comfortable, you can jump straight to 11.7 and do the mixed ones. Okay, so you don't have to do everything. If you're fine, you do the last one. If you're not fine, you do all of them. Okay. Any questions about the tutorial? No. Okay. Next, the quiz. Quiz, use your MCQ and the, the written. So I'll just make a note here. For the MCQ one, it's going to be the 10 integral series tests, 10 of them, with some of the words missing. Yeah, so if we go back to lecture 27, so let's say this one. Okay, so you're going to have that. Some of it's going to be missing. You need to fill in the missing parts. Okay, that's the MCQ. For example, this converges, that's missing. Then you need to select option A, converges. Fill that in. Okay, or for this one, maybe positive is missing, and then you fill that one in. Okay. Any questions for that? Okay, and then the written part, there will be 2 problems. Number 1 is just some series I just give you. Okay, I just picked it from the that 11.7. I just picked one. Okay, so you have that. You can use whatever you want to solve it. You can use as many methods as you want to solve it. Okay, it's out of 5. If you do 2 methods, you get 10 out of 5. You do 3 methods, you get 15 out of 5. Everyone okay with that? Yep. Okay, and then the last bit of the problem is a proof on series convergence. Okay, you have to look in the tutorials for that. Again, I just picked one from the tutorials. Okay. So you have seen it before if you do the tutorials. Okay, so one problem on showing if it converges or diverges, the other's a proof. So I'm telling you right now what it is. Okay. Any questions on that? No? So you know exactly what to expect. Any other questions before we go? No. Okay, next week we will start on Taylor series. Please read that chapter from the textbook.